And there are some common practices that I would like to mention here. Right. So first of all, it's a very these are very practical knowledge, and the choices for the parameters can change depending on what the problem is, what the actual data look like. Okay, so for the initial values, we basically randomize the parameters. Okay, and in this case, it doesn't really matter how so which specific way we randomize the parameters. But later on, when we have more features, especially more layers, if we stack the neurons into different layers, then the way of randomization or initialization also matters to the performance, to the behavior of the model. So we will mention that in the future lectures, but here just to notice that we need to keep this in mind. The initial values, they sometimes matters. And the next important question is, when do we stop the optimization, or when do we stop the gradient descent loop? Okay, so there are a bunch of different termination conditions we can use. Okay, like we can stop when the cost functions doesn't make significant changes, and we can define a some quantified standard in term to we can use some quantified values to define whether we think it is like significant change or not. Okay, and the third question is how big each step we need to take. So that is the question, a classical question of defining the learning rates alpha. Okay, so learning rates, in terms of learning rates, it is also a very practical question. So right now, in common practices, we often have learning rates pre-chosen by a lot of experiments in practices for certain tasks, like for the task of image captioning or image simple image classification on a certain data set, say ImageNet, then and for a certain type of model, say VGG or ResNet, we always have the learning rates recommended because people have done enough times of experiments to show that the learning rates should start with something. So this is an important question, and fortunately, we already have some empirical experience, knowledge about that. Okay. All right, and the last important question is how many data to include in each iteration. Okay, so in the example that we use for linear and for the simple linear regression and the multiple linear regression models, we implicitly use all the data in one iteration. Right? If we go back to the slide here, in each step we compute the gradients. We use the summation over all data points. Right? So when your data set is very big, that is a very expensive computation. If you have a 1 million data set, you need to sum up 1 million quantities each time you do the updates, right? That is not a cheap operation. So that is something we need to consider if we have large data sets. Okay. All right. Okay. All right. So in terms of how many data to use, we will define different types of gradient descent. Okay. So first of all, when to stop, right? We have various termination conditions. We can stop when a predetermined, predecided maximum number of iterations is reached. Okay, so I guess in the first few assignments for linear regression and the logistic regression, we simply set a upper limits for the number of iterations. That's something we can do when we do small experiments in data, right? We just want to see how the model, whether it makes sense, right? And in practice, sometimes we can stop earlier. So this early stop is used to avoid overfitting on training data sets. So it doesn't, so training a data set, it can be tricky because we don't want to fit, we don't want the model to overfit to the specialty of that part of data, but we want the model to be general. So sometimes early stop is a technique. Okay, we will reach that early stop technique later when we introduce the neural networks. Okay, it is more common to be used in larger models. Okay, or we can stop when the gradient itself is close enough. Okay, so because recall the shape of the quadratic function. When we reach the minimum points, the bottom of a quadratic function is very smooth. It's nearly to a flat line, right? So that means the gradients near that minimum point is also 0. Okay, so a good sign of reaching a minimal point is that our gradients become smaller and smaller. So whenever we reach a small enough gradients, we can basically be confident to stop at that point. Okay, or we can stop when the improvements, when the cost function doesn't drop enough. Okay, that's also some we can threshold, some standard we can use. And another way, we can use the performance of the model on some external validation data sets. Okay, so if the accuracy doesn't change significantly, then we can probably stop at that point. Okay, so these are just an early peak of knowledge that we will go through in future lectures, because we haven't talked about the split between training, validation, and testing yet. But here, since we mentioned we introduced gradient descent, I think it's good to have some ideas of the basic technique that we will deal with. Okay, and the second issue with setting up learning rates alpha, right? That step is critical, because if the alpha is too big, remember that now let's use the case for quadratic function again. When we want to update the theta 0 into theta 1, if the alpha is too big, then we might miss the minimal points because we moved theta to a point that's too far away. We go for a step that's too big, right? And if we go back into the next iteration, we just zigzag around the minimum points, but never approaching the actual minimum points. Okay, never converge to the minimum. Okay, but when alpha is too small, then it may just cost us too much time, right? Sometimes it's a balance to keep, right? The safe way is to start with some maybe smaller alphas and incrementally just gradually increase it, and you can observe the performance by printing out your loss or printing out your accuracy versus the iteration, and to see how that curve changes. Okay. All right. And speaking of the learning rates, there's one technique is that to adapt the learning rates value. Okay. So initially, the alpha to be 0.01 can be a reasonable initial value, but now I think my experience is that I don't know if this is true, because since the models becomes larger and larger, and really depends on the task, really depends on the model, okay? And the best way to find it is to look at people's results. When people publish new models, their papers, code coming out, and I think to learn from their experience is the best way to start. Okay. And the second important thing is that we want to adjust the learning rates when we are approaching the minimum points. And I just said before that the gradients will get smaller when it approaches a minimum. Okay, so the alpha, we also need to decay it along the process of training. Okay, because in here I said except for batch gradient descent. I will talk about this term later. We haven't talked about this yet. So basically, we want the alpha to be changed, to decay incrementally within process, because we want the steps to be smaller and smaller. When we reach the minimal points, if we take too much step, we will miss the minimum points. And we want our parameters to be as close to the minimum point as possible. That's the basic thought of adapting the learning rates. Okay, so there could be some time-based decay, right? When we reach the larger numbers of iterations, we decay the alpha, the learning rates accordingly, or exponential decay. So these are just practical tricks we can use. And nowadays we have packages handling this automatically for us, and we simply need to tell the optimizer that we want to decay the learning rates or not. Okay. So what if alpha does not decay? Then the worst case is that we miss the minimum points, or we didn't reach the most satisfying results out of the training. Okay, so finally, let's talk about different types of gradient descents.
Professor, I have a question about the learning rate.
Yes.
Okay, so kind of like I did the gradient descent before, and when I try to choose more features, I also realized the learning rate is going to have to be adjusted pretty well, especially when the dimension is pretty high, and I have to make the gradient descent really, really small. Otherwise, they cannot really converge. Is that also the case that we are going to worry about?
I think so. So when you said you have more features, basically more features means that brings more non-linearity into the model, because your model grows larger. Okay, so non-linearity means, well, honestly, it's more chaos. Okay, so you want to be more careful when there are more parameters to be tuned. So that's why I said I don't trust the typical belief that alpha equals 0.01 could be a good choice. In the recent bigger models, like the transformers, BERT models in NLP, I think if you want to pre-train the model from scratch, the learning rate is quite small, like 0.001, 0.005, something. So the issue you mentioned, I think it deals with the nonlinearity of the model. When there's nonlinearity, more nonlinearity, it's easier to skip the local minima. It's easier to miss the minima in the function. So that's why I think smaller learning rates make sense.
Okay, thank you about that.
Yeah. So now let's look at the gradient descent. I just mentioned the term batch gradient descent in a previous slide. So it is a way to compute gradient descent using all data in one iteration. That's exactly what we do in the slides for linear regression models, because we sum up across all the data points. Okay, so batch gradient descent it can be a choice when your data set is very small. Okay, in our assignments, we will use batch gradient descent because we only have 100 or so data points. But in most real-world machine learning applications, the data is big, and we need to partition the data into different batches. Okay, into different mini batches. So the advantage of batch gradient descent is that it is guaranteed to converge. Okay, so because the gradients will always become smaller and smaller, and sometimes if you use constant alpha, it still work. Okay, and the gradient estimated is unbiased because we are using all data. Okay, and it gives a straight strategy towards the minimum. It doesn't deviate a lot from the optimal path from the current position of your parameters to the theoretical minimum points. Okay, and because it is guaranteed to converge, but it utilizes all data, so it is not a very timely efficient method. Okay, so it is slow. So that's why we have mini batch gradient descent. That's something we use for larger data sets. So basically, in each iteration, we don't use all data sets or we don't use all data points to compute the gradients. We use part of the data sets called a mini batch, defined by the batch size. Okay, so the difference here is that we don't use the 2n, we use the batch size because we don't include all data points. And the advantage is that it's obviously faster, right? And also, if we randomly shuffle the data sets, it avoids that we use redundant examples in each iteration. Okay, and also it also brings some randomness during the training. It avoids some certain kind of overfitting. If we always use the same data to use the same batch to compute the gradients, it's kind of a overfitting to some fixed patterns. Okay, and the disadvantage is that it will not converge in theory because we're not using the globally accurate gradients. The gradients computed from a mini-match is some approximation. It is some approximated values with some randomness brought in. Okay, so eventually the cost function will wander around the minimum points in mini-batch gradient descent. Okay.
I have a question.
Yes.
So I guess, does this mean that when we talk about when to stop, so I guess if you're using a mini batch gradient descent, is that an example of why you would need to decide when you're going to stop because it could just wander around forever? And then in the batch one, maybe you would just let it run until it gets to 0?
Yes. Okay. That's correct. So for batch gradient descents, in theory, it will reach the minimum points. So you just let it work. You don't even need to worry too much about the learning rates. But for mini batch, there's some randomness when in each iteration it moves. So you need to set a smaller step as the training goes on. Yeah. So learning rate decay is required in the mini batch gradient descents. Okay. So if you look at the cost function, how cost function changes with the iterations, the batch gradient descent basically shows some a smooth curve, but for mini batch, there's randomness between different batches. So there's some more jittering in the curve. I've got a question. Is there a convention for selecting the mini batch size? One convention is that people like numbers that is 2 to the power of something, like 64, 128, something. And the size of mini batch also decides how accurate the gradient descent is. So basically, you don't want the mini batch to be too small, because if you sample the too small data points, then there are more randomness in the gradients, right? You want a mini batch to be bigger if you want the learned gradients to be accurate. But sometimes when a mini batch is too big, the computing is slow, because if you also the memory of your GPU is also limited. It doesn't accept a batch that's too big. Okay, depends on the data. If your data is like a very high dimensional, then the mini batch cannot. There's always a limit.
Thank you.
Yeah. Okay, so the last type of gradient descent is called stochastic gradient descent. Okay, so there's a misunderstanding nowadays, or like misuse of this term in a lot of places. So strictly speaking, stochastic gradient descent must use one example to compute gradients, right? And then perform the updates based on the gradients from that that single example. So of course that brings a lot of randomness, because that's just the conclusion. That's just the information from one data point. It doesn't represent the patterns for other data points. Okay, but the advantage is that it's easier to compute, right? And because it brings in more noise in the learning process, so it might help the model generalize better. But the cost is that the training is much slower. Okay, and I don't think people nowadays use stochastic gradient descent like the strictly speaking, the strictly defined stochastic gradient descent. But we in some papers, some code, for example, in PyTorch, it provides a optimizer named stochastic gradient descent, SGD optimizer. But that optimizer still, you can provide a batch size to it. Okay, so I don't think we need to worry too much about the term. So it's basically the same thing, but the idea is that it really depends on how much data we have and how fast we want the training to go, right? All right, so that's 3 types of gradient descent. And if we use some intuitive comparison for how fast the gradient drops, it is more like this. So if you use stochastic gradient descent, there's more randomness indicated by the purple. And for the batch, it is always smooth. And mini batch is somewhere in between. I saw a question, is it that the accuracy using mini batch would be better than batch gradient descent? No, in terms of the model performance, the batch gradient descent will make sure that you reach the minimum points. It is not that the mini batch would have a better accuracy. No. So the model's performance can be measured by the accuracy, but the gradient descent method depends on how fast or how efficient the training process is. So maybe with batch gradient descent, it will reach the minimal, it will reach the theoretical minimum points. It is guaranteed, but mini batch methods can also reach to the some point nearby, which brings no difference in terms of model performance. That is also possible. All right, so other tricks, I mentioned one point here. We can, that is actually give me a second, please. I'll be right back. Okay, so this trick, I think I have done it in the assignments because the data, when they are normalized, it's easier for the gradient method to find the best way, to find a more efficient way from the current parameter values to the theoretical minimal points. And I think that's it for the course today, for the lecture today. And the key points is about using gradient descent algorithm to solve the linear regression models. So this is a very general paradigm I've shown here because it doesn't apply, not just apply to linear regression, but all kinds of models here. No matter it's shallow models or deep models. And we will apply more, basically modify these paradigms by introducing different kind of techniques, like the mini batch technique, which we will mention more in the future, and also like before and after each batch, we can do normalization, we can do all kinds of regularization techniques in order to make the training more robust and more efficient. And that's the contents of the course. And you can ask questions now or leave questions in my email. And one thing we need to decide is to choose another office hour time. Okay, because right now this time has been used for the lecture, and we need to decide a time. So I will probably send out a Google poll, something like that. You decide what time is the best for you. Hopefully I can choose the best time for everybody. But if there's conflicts, I will do my best to avoid conflicts in your schedules. Okay. And thank you everybody for coming. I will upload this video in the afternoon, and there will be 1 or 2 quiz questions about the course contents, and just feel free to check the Canvas updates.
Professor, I have a question.
Yes.
In regards to, you had mentioned earlier with gradient descent that you need to calculate both of the thetas simultaneously. Does NumPy do that automatically, or do we have to declare our intent with when we're programming?
So in our assignments, I think we need to do that intentionally. And the NumPy handles only, NumPy is just a container that stores data for you. But the way you compute gradients in the assignment 1 is that you need to manually compute those gradients. But for actual real world usage, nowadays the gradients are basically automatically computed by the package like PyTorch, like Tensor, and basically you don't need to worry about the simultaneous updates issue. Okay, but I think it's good to know that we need to update the parameters carefully.
Okay, thank you.
Yeah, there will be a quiz due. No, not due today, but I will publish the quiz. I will release the quiz, and it'll due in 2 days, or actually 3 days. Yeah. Yes, due on Friday. So thank you, everybody. I gotta go. And let me know if you have any questions, if you have concerns about office hour time. I will send out emails about office hour later. Thank you, guys. Good to see you guys. Take care. Bye.